Welcome to another video of Stat 420. Today we're going to talk about different probability functions in R. So I'm going to get RStudio up here on the screen. And there's four different types of functions that we're going to talk about that we'll commonly use. And then the letter at the front is kind of the identifier for what the function's going to do. And then the name of the distribution is identified second in these commands. So, so here is dnorm, but just kind of as an FYI, we could also do dt for the t distribution. We could do d chi-square, or there it is, d chi-square for the chi-square distribution. So that part can change. The d at the front does tell us what it's going to be doing with this information. So the d function is going to produce the height of the density curve. So for example, if I was working with a normal 0, 1 distribution, and maybe my data point is, we'll just say 0, then I'll do mean equals 0, and I'll do SD equals 1, and then this is going to output to me the height of the density curve at that point. Now, when we're working with continuous data, just keep in mind that this does not mean that there's a 39% or 40% probability that I'm going to get the value 0 from a normal 0, 1 curve, and that's because continuous data doesn't produce a probability at a point, but produces a probability at a range. So in that sense, the d function isn't super helpful with continuous data unless I'm just like trying to plot the density curve or something like that. So if I were to simulate dnorm for, a sequence of possible values and then create a histogram or create a scatter plot, I guess, I could kind of recreate the normal curve. But other than that, there's not a whole lot of use in the case of a continuous distribution. More likely, I'm going to be using something like pnorm. So pnorm is going to find the probability to the left, or if I choose to do so, to the right, of whatever point I've listed. So with pnorm, the first value that I plug in is going to be q, which is going to be a value. So let's say that my value is, I'll just do 0 again for sake of example, and then I'll change it. And I'll do a 0, 1 normal distribution again. And this is going to be giving me the probability to the left of this data point. So since I picked literally the mean, then half of the distribution is to the left of the mean in a normal distribution, because the normal distribution is going to be symmetrical about the mean. If I were to pick a value that's a little bit lower, like -1, the probability is going to be less, right? So less the data is below -1 when I have a 0, 1 normal distribution. Same thing if I had a positive number, but going the other way now. So now most of the data is going to be to the left. Now there is an option that I could choose lower dot tail equals false or true. So if I'm choosing lower dot tail equals true, it's going to work exactly as it's working right now. But if I change this to lower tail equals false, then it's going to give me the tail area now to the right. So instead of the lower tail, it's going to be giving me the upper tail. You know what? I need to move my picture out of the way because I am in the way here. Let me put myself, I don't know, I'm going to put myself way up here for now because this is probably not a very important spot at the moment. Okay. So qnorm, we're going to continue on here. Data associated with the probability plugged in. So in this case, I plug in a probability value, but now I'm going to get out the data value that would be associated with that point. So it's kind of the opposite of pnorm. It's like the inverse here. So if I do qnorm, I'm going to do this. I'm going to do a normal 115 distribution so that I'm not just working with zeros and ones again, because that's probably confusing. So let's do, let's say that I have the data point 90. Or actually, I need to go with the probability. So let's say the probability I'm interested in is 0.3, and I'm working with mean equals 100, standard deviation equals 15. So this is going to tell me the data point such that 30% of the data is less than that point. So apparently 92 is the value such that 30% of the data is less than this value in this distribution. And obviously, if I pick a probability more than 50%, then it's now going to be above the mean. Again, since the normal distribution is symmetrical about the mean. And then, by the way, I guess I'll go ahead and do the inverse here. If I were to plug in 92.13 approximately, but same information, but now I'm going to do the p-norm, I should get back 30% approximately. So again, it's the inverse. All right, so rnorm is another command that I can use, but this one's going to be a little bit different now because this is going to actually produce to me a random set of values from the distribution that I describe. So the first entry here is going to be the number. It's going to be n. It's going to be the number of points, the number of, we'll call them data values that I want to produce from this particular distribution. So let's say I want to produce 50 data values, and I want it to come from a normal distribution with mean, we'll say mean 10, and we'll say standard deviation 2. And so now I'm going to get 50 data values from this described distribution. I could obviously do more. I could also save this. So more commonly what's going to happen is if I'm using this, I'm probably saving it under something and using it in some other function later. So I could save that, and it's going to appear up here. Again, my head is again in the way. Oh, you know what? I don't need to see my files pane. Let me put myself way down here because this is not, that's weird. I'm just like floating over here. I'll put myself all the way in this corner. That makes a lot more sense. All right, so now I've saved this under sample, and it's just going to show up in my global environment now. So that would be something I commonly do when I run like an R something. All right, let's look at this was a PDF, so a probability density function. But what if I have a PMF, so a probability mass function, where I have discrete values like a binomial distribution? How is that going to change things? So I'm going to do this with the binomial distribution real quick, and you'll notice that that for D binomial, this is going to make a lot more sense now because I do actually have a probability at a given point. So if I'm working with a binomial distribution where the probability is 50% and I'm running 20 trials, then this right here is going to tell me how often I should expect to get exactly 8 out of 20 successes given my probability is 50%. So I can run this, and I'm going to get about 12%. So it means that about 12% of the time, I should be getting about exactly 8 successes. I could do this with different values. So I could do it with 10. So 10 would be the expected value. It would be the most common value in this scenario, and that maxes out around 17.6%. P binomial will also work. It's going to find the probability below this point. I'm actually trying to remember off the top of my head. I'm trying to remember if it includes 8 or not. So I guess I can test this out. So if I put in 1 and I get some value, but then I'd have to do 0 to know for sure because it's possible to get 0. So I still get a value, so I think it must include the value that you plug in as well. And I guess I could also find this out if I plug in 10, because then I would get slightly more than 50%, which I do. So it's going to be the value up to and including the value that you plug in there. Q binomial is going to, again, just be the inverse. So I plug in a probability and I find the value such that the tail probability is equal to that value. So if I plug in 25%, I get 8. So that means about 25% of the time I'm going to get a value of 8 or lower in this distribution. And again, I can take a random sample of observations from this distribution. So if I run 50 of these, so if I basically think of it as like flipping a coin 20 times and recording how many heads I get, these are the random sample options that I get. So sometimes I'll get 9 out of 20, sometimes I'll get 14 out of 20, 13 out of 20. So, and I can even plot this, by the way, if we just want to look at how this kind of turned out. Oh, now I'm in the way again. Well, I'm not, I'm probably fine over there. So I can get a histogram to see kind of what that distribution looks like. And I can see that, well, I'm kind of in the way, but in general, I'm getting values a little bit closer to the middle, not perfectly though, because I only sampled 50. If I were to sample a lot more, like 5,000, I'm probably going to get a much more normally distributed curve here because the binomial distribution is going to kind of converge to the normal distribution with enough observations. All right, so hopefully that's helpful. It was just kind of a short introduction to those, but yeah, we'll be using these commands a lot throughout the course.